It's now time for our second lecture, and this is by Leifur Leifsson, who heads the laboratory for unmanned vehicles here at Reykjavik University. And it's interesting to note that this year we are basically expanding Cadia, which actually originally Cadia always meant to be an interdisciplinary center for research. But we are kind of taking it literally now, and Cadia is becoming an interdepartmental center for research at Reykjavik University. And our largest step to date is to basically bring in people from the School of Science and Engineering, which Leifur is a part of, and also School of Business, the Department of Psychology in the business school. So this year we are really seeing big changes in Cadia, and we are absolutely confident that this will bring a lot of new life to research at Cadia and bring us to new places. So here we have Leifur, who's going to give us the glimpse of the kind of things that will be happening in Cadia with the participation of his lab.
All right, thank you very much, Hannes. So my name is Leifur. I'm an assistant professor at the School of Science and Engineering. And so I'm a head of this laboratory for unmanned vehicles. Like you said, we recently joined Cadia. But so today I'll talk to you about the vehicles we're working on, the research projects. But I guess you can say we're kind of doing the hardware part, whereas, for example, Chris is doing the software part. And so most of the things I'll show you is just different types of vehicles that we've been working on up to this point, and hopefully in the future we can do some work with the computer scientists and add some intelligence to these vehicles, or they can use them as a test bed. So, there's been a rising interest of engineers on unmanned air vehicles. Here are some examples that people are working on. For example, the Global Observer that can fly with just solar power. These are kind of big aircraft, but the interest is more towards smaller vehicles, like the ones you see here, the Delphi, which is very, very small and flies with a flapping motion. Also these quadcopters or multi-rotor vehicles, different types of flapping mechanisms like the hummingbird or the spybug. Actually, this spybug can't fly. But so the engineers are interested in these things, and they're interested in developing engineering methods to design them. So we want to understand how we can design these aircraft, because we've been designing aircraft for 100 years, but it's mostly been focused on large aircraft that fly at a high altitude and fly very fast. But when you want to go small and slow, actually traditional engineering, aircraft engineering, it doesn't work. So if you look at this graph here, you have mass on the vertical scale, and you have Reynolds number on the x-axis, which is basically saying type of forces what you're acting on the vehicle. So for a large aircraft like the Airbus A380, mostly you have inertia forces working on it. But when you go smaller and you want to go towards like insect sizes, different types of forces start working on these vehicles, more viscous effects. And then different types of mechanisms are, for flight, are becoming more efficient. For example, like flapping. So what we're working on is somewhere in the range of large birds or micro air vehicles. And we're talking about aircraft with wingspans less than 15 centimeters, weighing less than 100 grams and traveling 20 meters per second. And you want to do this for at least 20-30 minutes. In the future, the engineers are, or the common goal is less than 8 centimeters in wingspan. So that gives you some idea of this sizes that we're working with. So obviously, hardware like batteries, computers, and such things have to be miniaturized. The potential usages of, for example, is surveillance, of course, and nature watch. Using images, video, law enforcement, border control, some type of security enforcement, using some type of sensors like for weather measurements, pollution, or ashes. You can you can measure ashes in the air around volcanic eruptions. Search and communication. There's a lab here, systems lab, that's working using these types of aircraft to set up like a communication system in disaster areas. And we plan to work with them. And then, for example, if you want to use these UAVs to reach open areas which are hard to or difficult to reach inside buildings, for example. Other could be transport or placement of sensors, exploration on Earth or even other planets. These vehicles have to work in different geographies, surroundings, for example, within a city, between buildings, between cars, around people, or it could be in the mountains or a glacier or even forests. It has to adjust to the variable wind speeds, gusts, and temperature. It has to have some obstacle avoidance systems to navigate around buildings or people or such things. So there are a lot of requirements for something like that. And when you want to decide what type of vehicle you want to use, it really depends on the application. So, for example, if you're looking at a city like this, you can roughly divide it into two spaces, open and tight space. For some open space, you want to cover a large area, you might want to use a larger type of aircraft. Has a lot of battery power and can cover a large range. But looking at tighter spaces, you might want to go to something like this, a rotorcraft, or even if you go to tighter spaces, you might want to use it, or even a type of flapping wing vehicle might apply. So obviously, if you want to cover a large area, you won't use a flapping wing vehicle. So it's not very efficient. So what we're doing is actually, the main project is a flapping wing vehicle. So something like this. And we want to be able to fly it with flapping for cruising, for different types of speeds. So you can look at this Falcon there, and you can imagine that it has actuators inside of it, a computer on board, and you have these wings that it has to control. It can do gliding, which is something that the other vehicles can't really do. It can do hovering as well. So there are a lot of applications you can use, these different applications for these vehicles, if it can do these things. And also for energy efficiency. You want to be able to take off autonomously and even landing autonomously. So you want to have autonomous aircraft. That's having a snack there, actually, as well as diving. So that's actually one thing we want to do. So the way we're doing it is kind of looking at a mechanical arms like these. And obviously this motion is quite complicated to be able to control it and to manufacture the parts for it. But we started with something simple. So we have a simple mechanism like this one here on the bottom. So we're building various types of actuation systems because this is a big problem, just actuating, going from the battery to the rotors to the wings. It's a big problem if you want to do it efficiently. This is the simplest one we did so far, and we're implementing it. But there are various types of other types that we're working on. If you're able to actuate the wing, you can control the wings, you can control the tail. You need to actually control the vehicle itself on flight. So a control system is essential. So what we did here is we got a commercially available ornithopter and an autopilot system, and we inserted the autopilot system on board. And so the wing, the ornithopter works like this. You have to kind of pitch up to get the lifting force, and then you just have a motor driving the flapping. The tail is just used to kind of navigate and control it. But then, so you can get these, you can do a remote control on it, but what we managed to do is put an autopilot on board, so it's actually flying by itself, navigating through just GPS points, and at the same time trying to hold angle and direction. But obviously, this becomes very, very difficult when you want to do it really fast. So, for example, with smaller and smaller vehicles, you can look at birds that move really, really fast. So you have to have a really efficient mechanism to do that. So in this development, we have various types of vehicles that we want to develop autopilot systems, sensor systems, and such things. And here are a couple of examples. So that's just a regular aircraft with autopilot system on board and a camera. So this is actually easy. The technology is just available. You can buy it online. But assembling it and making it work is actually much harder than we thought. But you can imagine these type of vehicles are actually very useful. Just having a camera in flight is very useful for many things. For example, like search and rescue. I mean, that's actually essential. So when you have a big search party, okay, and you want to look at a big area, just getting eyes in the air is essential. So another thing here is these quadcopters, which this one has 4 rotors, and it's fairly noisy and needs a lot of power, but it can carry like 3 kilos. So you can put a lot of batteries on it, or you can use different types of sensors. And for now, these are just the kind of initial things. They can hover and hold position. We've flown them outdoors. They can fly up to 50, 100, 200 meters and just hold position. That's easy. Another one is this same type of aircraft is a weather measurements and weather forecasting. So on board this vehicle, we put temperature sensors, humidity sensors, and so forth. We can collect this data and use the data then to do very precise forecasting of the weather in local areas. This is very useful for example, for search and rescue. Here's another thing that we worked on in collaboration with a company called Cadia. This type of vehicle is like a torpedo vehicle. So I'm moving on to water now. And this vehicle just has the thruster at the end, at the back, and really has to have some speed to be able to control itself. So what we did, we did some kind of low-speed control systems for this type of vehicle. We put sensors, or we put thrusters on the side, and we can do like surge control, kind of sideways translation. We can do yaw control as well, controlling the attitude of the vehicle. And so then this vehicle is actually commercial, so you can actually go and buy it. It's pretty expensive though, but yeah, so we're working on stuff like that, on control systems. And just to end this, we're also working with a professor at the University of Iceland for biology research. We actually developed a new module for this vehicle. We put a camera on it, so we can do high quality photographing of kind of bioorganisms on the water bed. And what they use it for is just counting and looking at these organisms. So that's the lab, all the crew members. Most of them are students here. We only have one computer scientist, but hopefully we can get some more computer scientists to do some software development. But most of these are engineers, mechanical or electrical. Also, Hjalti and Indri are faculty members here, and some other outside researchers. Thank you very much.
Many of the vehicles have limited space, not sure. How do you cope with failures? For example, in an engine or some kinds of parts?
If motor fails or something like that, it'll probably just crash. So that's actually right now there's nothing, there's no kind of safety on board that. We haven't covered that area, I guess. But some of them you can, of course, in theory, you could have some type of a system control that might, for example, just have it glide down or something like landing, something like that. Obviously, you can't do it for rotorcrafts. So this is an issue. Safety is one thing, but right now it would just crash.
I was also wondering about the flapping wings. Can you actually make the head completely stable for like putting cameras in the head for sight? I mean, it feels like the whole thing is
it's
moving a
moving.
lot.
Yeah.
Is that a difficult thing to create a stable vision, for example, for a flying vehicle?
Yeah. So when it's moving like this, it's applying inertia like forces to the vehicle, so it's kind of moving like that. But I think it comes down to the control system and the actuation system. If you have it smooth enough, and then you can control it as well through the control system, then I think it's quite possible. But also there are camera systems that you can kind of negate this kind of movement as well. So yeah, you should be able to get a good quality video footage, I think.
Question from over there. Last question. Is there a question there? Yes.
What about efficiency compared to propellers?
Okay, so the one I showed you, the ornithopter, is very inefficient. Doesn't make any sense to create this aircraft to use it, because you can use a fixed wing aircraft for propeller, much more efficient. But there are researchers working on this, and they look at the aerodynamics of these things, and they actually compared rotors versus flapping, and when it comes down to scales of like 10, 20 centimeters or something like that, or less, then they've shown that flapping is more efficient motion, just because of the different scales of forces that are acting on it, even better than rotorcraft. So although we're starting with these big vehicles, we're doing it because we can buy off-the-shelf parts. We don't have to develop everything from scratch. But in the future, we want to move to something smaller and smaller.
Last question.
First of all, I love what you're doing. Great work.
Thank you.
One thing I would want to see this technology is in, for example, a regime like in Syria. If they use this technology, that would be a disaster. In the future, I don't want to see.
Well, most of this technology is available now. So you can go online and you can buy.
Use this for many bad things, I think.
Of course. So these things are available now, and people can do this. So a lot of things I showed you, we bought online. We just assembled it, and a lot of people do it. So yeah, there is always a potential people could use it for bad things. But that's just the.
If I may add one thing to that, if you're interested in the ethics of robotics and AI, take a look at the Cadia clause, which is something we put on all software in the HumanOps project.
Which is what?
Which is an addition you can put on your software license or license for anything really that addresses some of these concerns.
Thank you very much.